Welcome back to my channel, Maithili SK. In this session, I'm going to handle you Dsb-Sc-Am, that is double sideband suppressed carrier AM. The agenda for this session is why we go for double sideband suppressed carrier AM is explained. Followed with that, I'll explain about the mathematical representation and generation types for Dsb-Sc-Am and detection for the same. Now, why we go for Dsb-Sc-Am? So we know the amplitude modulated signal has three components, that is carrier, upper sideband and lower sideband, along with two, that is upper sideband, lower sideband and carrier. So now coming to the point, when the modulated information, that is modulated wave, is being transmitted, we find that the information is contained only in the sidebands and no frequencies or nothing is transmitted through the carrier. So carrier is an ideal one which is being transmitted from the transmitter end to the receiver in case of double sideband full carrier, that is the basic AM signal. So this is the plot we will be seeing when we go for this next case of double sideband suppressed carrier AM. That is, here we have the sideband, carrier and upper sideband. So when transmission is happening, this position, that is carrier position, is also transmitted along with this upper sideband and lower sideband, which is not necessary. So in order to save the transmission and make it efficient, we are going to suppress this carrier part and see how the transmission is happening. So now here we are going to remove this part of carrier and we are going to transmit only this upper sideband and lower sideband. Hence it is called as, which contains the sidebands, both the sidebands, so it is called as double sideband but no carrier. So suppressed carrier amplitude modulated signal. Hence the name arrived so. Now we'll see the mathematical representation of Dsb-Sc-Am. So let us consider the mathematical equation or expression for both modulating and the carrier signal. So modulating signal is represented by m of t in terms of voltage Am cos omega mt or cos 2 pi fmt, and carrier signal is represented in terms of AC cos omega ct or 2 pi fct. Mathematically, we can represent the equation of Dsb-Sc wave as the product of modulating and carrier signal. So, it is simply multiplying these two signals of carrier as well as message signal. So, I am just multiplying the input. What happens here is we will get AM cos omega mt and AC cos omega ct. So, finally, when solving this, we will get using the trigonometric function, we'll get the terms. So don't get confused, it is the same term which I have shortly written here in terms of omega ct, right? So previously it is noted in terms of, this term is noted here as 2 pi fc and this is represented as 2 pi fm. So here t is missing, it should be t, right? So you could see here, instead of that, we can write this as omega c as well as omega m. That's what I have written. So solving is, by previously we have solved this, no, that's the same case by using cos a cos b formula. We are going to solve this, means it will be obtaining in terms of 1 by 2 cos of a minus b plus cos of a plus b. So this is the term we are going to get. So that's why I have written in terms of here, a here term is 2 pi fc and b term here is 2 pi fm. So I have shortly written as omega c and omega m. So finally we have arrived at these two cases of, just by arriving at a product of this term, we have obtained the lower sideband and upper sideband. So this is the final mathematical equation for DSB suppressed carrier, that is double sideband suppressed carrier AM. Now coming to the bandwidth part, this is, as we know this with respect to the spectrum, it has a lower sideband and the upper sideband there is no carrier. Though there is no carrier, the frequency terms is represented in terms of Fc, and here it is represented in terms of Fc plus Fm, and here it is Fc minus Fm. So it is the bandwidth contains between these two signals, that is twice of Fm. So that is what we have arrived at bandwidth. Next, coming to the power calculation, we know the power calculation, we need to consider the same equation, final arrived equation for Dsb-Sc-Am by mathematical derivation. Take the same term. So here also T is missing. So just represent the same. And here we know the total power is nothing but the power contained in the frequency, that is component present in the signal. So what is the the component present here is only the lower sideband and the upper sideband. So power contained in lower sideband plus power contained in upper sideband gives the total power of the double sideband suppressed carrier AM wave. So we know the standard formula for power of cosine signal is, that is cos signal here is, P is nothing but Vrms square by R. That is, we know power is nothing but V square by R. So instead of this V, I am taking in terms of a root mean square value. So I am going to take this voltage level. So here the voltage level is nothing but the product, that is which is present above the near the uh, lower sideband and upper sideband. So here the voltage parameter or metric is represented in terms of AM AC by 2. So instead of this volt VM, we are going to substitute here AM AC by 2 divided by square root to the whole square. So when solving it, we will be getting the term as AM square AC square by 2, square root of 2 is nothing but 2 into 2, that is 4. So here already we have a 2 here. So we are getting 4 into 2 is 8. So we are getting 8A, that is AM square AC square by 8R for one sideband. So it is, since we are having the same term for the previous next also. So this term is common for both upper sideband as well as for lower sideband. So I am going to represent the same equation of AM square AC square by 8R for next lower sideband too. So now coming to the total power is nothing but just adding the upper sideband power and lower sideband power, that is nothing but 2 AM square by AC square by 8R, cancelling it become AM square AC square by 4R. So this is the power calculation equation for double sideband suppressed carrier AM. Now coming to the next part, that is Dsb-Sc-Am generators and detectors. We have two type of generators. First one is called as, just we know from the basic equation itself, it is nothing but the product of the two inputs we are feeding into the modulator. So here by feeding a message signal and carrier signal, just multiplying it produces an output of Dsb-Sc-Am. That concept is explained in balanced modulator. It is also called as product modulator. And the next case is the ring modulator, which uses 4 diode cases of D1, D2, D3 and D4. And next is a Dsb-Sc-Am detector or demodulator, where we will be using a coherent detector. The meaning for coherence is nothing but the signal which is we are using is synchronized with respect to the signal whatever we are used earlier. Next, we are under the coherent detection, we will be having the Costas loop receiver. So we'll see one by one. First one is the balanced modulator. So for balanced modulator, it consists of two identical AM modulators. First AM modulator 1, AM modulator 2. So as we know, just by adding the signal, we will be getting the double sideband suppressed carrier AM. That attempt is made here. So S1 of T produces the output from the modulator 1, where the message signal is fed from directly to this one, whereas the local oscillator signal is fed through a common local oscillator which gives a carrier signal. So finally it produces a modulated output, that is AM modulator 1 output in here in the first case. The next case, since we have to produce a lower sideband, we are reversing this message signal, that is negative signal of the message is given here and it is given to the product modulator which just multiplies to give the output of S2 of t. Finally, these two are added. Here we will be getting the upper sideband and here we will be getting the lower sideband. So both these signals are added together. So here when added we will be getting upper sideband and lower sideband. So we have obtained only the double sideband case here. So that is what explained equation in equation format with respect to carrier signal which is taken at the center and it is fed to both the modulators. Message M of t is applied with respect to positive and negative polarity. So here you could see here the positive and negative polarity which is enhanced to give the output. So in case of S1 of t and in case of S2 of t. So finally we get the S of t for the first case when subtracting and next case by taking a positive value with respect to negative inputs. So finally when we add these two signals S1 of t and S2 of t, we will be getting equation which contains only the product of these two terms, which is nothing but with respect to message signal and the carrier signal. If we just solve it, we will be getting both the upper sideband and lower sideband signal. So by comparing the output with respect to the summer block with standard equation of double sideband suppressed carrier wave, we will be getting the scaling factor here we are using here is twice that of the Ka. Next, coming to the next type of the Dsb-Sc-Am generator is the ring modulator. So ring modulator is nothing but why it is called as ring means here four diodes are connected like in a circular pattern or a ring pattern. Hence it is called as a ring modulator. So DSB modulator is also called as product modulator as we have mentioned earlier. This is the structure of the ring modulator circuit where two center tap transformers are used to give the input to the balanced modulator. So here the message signal is fed to one end of the input, whereas the carrier signal is taken between these two transformers, that is here this is the transformer 1 and this is transformer 2 to give or feed between the two modulators structure where we have seen in the earlier case. So similarly, now we are going to see how this message signal and carrier signal will be operated to produce the output. So now the message signal is applied to the input transformer as I said and the CT is applied between the two center tap transformer. So for a positive half cycle, we know the message signal will be contained in terms of a sinusoidal signal. So for this positive half cycle, we can say this diode D1 and D3 are on state and whereas D2 and D4 are off state. For the reverse case, this case the diode D2 and D4 are the reverse process. D2 and D4 are on state and D1 and D3 are off state. So in this way the message signal will be, that is the first case, we will be having the positive peak, no? So that is here the signal is multiplied by 1, whereas for negative case the amplitude level, if I am taking it as -1, it is multiplied by -1. Hence there will be phase shifting with respect to DSB when it is starting with a negative input. That is what explained here. So from the above analysis, we can say that four diodes D1, D2, D3 and D4 are controlled by the carrier signal. So if the carrier is a square wave, then the Fourier series representation CT is represented as. So with respect to square wave equation, do remember with the signals and systems concept, here we have considered only the final equation format, the general format for a square wave signal. For a square wave signal which is represented in terms of 4 by pi summation n equal to 1 to infinity minus 1 whole power n minus 1 divided by 2 into n minus 1 cos of 2 pi fct into 2n minus 1. So we'll get the double sideband suppressed carrier wave S of t, which is nothing but the product of the carrier signal and the message signal. So now we are going to multiply this with respect to this is actually the C of t signal. So now just multiplying this with the message signal, we'll be getting the double sideband suppressed carrier equation, which is obtained at the output of the transformer. That is the operation of the ring modulator. Now coming to the detector part, we have two types of detector. Basically, we have a detector part which is called as a coherent detector. Here two detectors detection process is explained with respect to coherent detection followed by the Costas loop receiver. Now we will see the coherent detector first. The coherent detector or synchronous demodulation part is explained here. The baseband signal can be uniquely recovered from the Dsb-Sc signal by first multiplying it with the locally generated sinusoidal wave and then filtering the output product. So it is assumed that the local oscillator signal is exactly coherent with or synchronized. We can say it is the same as that of the signal which is having with respect to carrier signal. So the local so this local oscillator signal produce a carrier signal which is exactly in coherence with the input signals. Hence it is called as coherent detection or synchronous demodulation. So this is the exact figure of the coherent detector where input, that is here we are talking about detection part. So we will be fetching the input to the product modulator from the output of a DSB signal. So DSB wave which is generated is fed as input here, and you can say here a local oscillator is used to generate a carrier signal. So the carrier signal is fed here. So it's to the product modulator. We know the product modulator is nothing but which just multiplies here. S of t into C of t is given here. So we will be getting the two waves. Actually, double sideband suppressed carrier AM has the upper sideband and lower sideband here. The upper sideband and lower sideband signal which is having the message content here. So when we are multiplying this with the carrier signal, it produces both the carrier signal as well as the message signal. So finally, fine-tuned low-pass filter is used to reject the unwanted signal and just to get the message signal. So this is what the process happens in a coherent detection. That is explained with respect to the equation over here with respect to the diagram. So as we have mentioned in terms of equation is given here with respect to S of t and C of t. So just by multiplying this, we'll be getting the output V of t. So V of t we are going to substitute the values with respect to the S of t signal and C of t signal what we have considered. So finally arriving at the equation which is having the two terms. The first term is a scaled version of the message signal and it can be passed through the low pass filter. Finally to reject the same, and we will be getting only the message signal which is a demodulated output. So we want only the message signal term which is finally obtained by passing it to a low pass filter. So the demodulated signal amplitude will be maximum when the phase 5 is 0 degree, and we can say the demodulated signal will be 0. So either the peak value is happening when phi is equal to 0, and it will be 0 when this phase angle is plus or minus 90 degree, and this effect is called as quadrature null effect. Next is Costas loop receiver. The figure below shows the Costas loop receiver where we can say here two product modulators are used. So we are going to get two case of modulation output with respect to here. There is V1 of t or S1 of t is taken here. So the message signal M of t, that is what we are obtained from the suppressed double sideband suppressed carrier AM is fed to the product modulator. We know for a modulator we have to feed the message signal. If this is taken as message signal, the carrier signal is to be fed. So for this case, we are having a local oscillator, voltage control oscillator, where it produces direct input to the product modulator 1 with respect to carrier, whereas here it is for the second modulator case it is phase shifted and fed as input. Finally, this will produce two cases of product output with respect to message and carrier. Here one case, and here also we will be getting the second case of output with respect to the product of the same with respect to input. Finally, passing it to a low pass filter, we will be getting two terms with respect to message signal, and that is given as an output after passing it through or selecting only the wanted signal. So then we'll be getting actual demodulated output, which is nothing but the message signal. So Costas loop is nothing but which consists of two product modulators with a common input S of t. That is what explained previously. So the two equations are considered here with respect to message signal, where S of t is nothing but the actual signal which is containing the upper sideband and lower sideband. So the final output when the DSB equation is taken here, and the voltage control oscillator output for the upper modulator is considered as cos of 2 pi fct plus 5, whereas for the second case it will be different. So the first case with respect to V1 we are going to see with the upper product modulator with respect to input S of t and C1 of t. We are going to substitute the case of S of t from the input signal, and getting as a product case after simplification we will be getting two terms with respect to message signal and a scaled version of the message signal. So solving it, we will be getting for the first product modulator output, which is in terms of EAC by 2 into cos by m of t. So that is only the message signal is obtained. So this is a scaled version for the first case of the modulator, product modulator 1. So for the next case with respect to 90-degree phase shifter, we will be obtaining the case of 2 pi cos of 2 pi fct plus 5 in minus 90-degree phase shifter is given, means it will give a sinusoidal output which is having the output like sine of 2 pi fct plus 5. This signal is applied as a carrier of the lower product modulator. So V2 of t will be is nothing but S of t into C2 of t, whereas C2 of t is nothing but with respect to sine 2 pi fct plus 5. Now solving the same with respect to product modulator, substituting the same, we will be getting the two terms with respect to m of t. So again this is the scaled output. So we will need only the message signal. So it is passed through the low pass filter under the necessary signal, that is the message signal is obtained as the output. So this is about the Costas loop receiver. So these two low pass filters are applied as the input to the phase discriminator. So what is phase discriminator is nothing but based on this phase difference between these two signals, the phase discriminator produces a DC controlled output. That is, one is with respect to positive and another one is with respect to negative based on the phase shift happening here. This signal is applied as the input to the voltage control oscillator to correct the phase error in the VCO output. So therefore, the carrier signal used for Dsb-Sc modulation and locally generated VCO output, finally it will be in phase in that case. Hence it is called as Costas loop receiver, where it is trying to make in phase with respect to the signal. So this is about the Dsb-Sc-Am detector, the second half. So today we have covered Dsb-Sc-Am. This is coming into picture for preserving the power and bandwidth case. So in order to avoid a carrier which is not doing nothing in the transmission, we are going to suppress it. So only two sidebands are transmitted. So this is understood by recalling the spectra of the AM signal. So power calculation of DSP with respect to two sidebands are calculated, which is nothing but in terms of VMVC square by 8R. So generation part is now explained with respect to two methods. So generators, please do remember it has two types. One is balanced modulator and second one is the ring modulator. In deduction part, it will be having two again, coherent deduction and Costas loop deduction. So when coming to the university question, they can be asked like this. So they will be asking to draw the spectrum of Dsb-Sc-Am. Also, they can be asking what is the bandwidth of Dsb-Sc-Am, what is the total power transmitted with respect to DSB signal, and what is the power saving of Dsb-Sc-Am. This one we'll see after SSP signal. So this is still pending now. We'll be calculating the power. And what are the types of Dsb-Sc modulator part? So as I said, it is two with respect to balanced modulator or product modulator, and next is the ring modulator. Please do remember. And DSB demodulator, again it has a coherent or synchronous detector and Costas loop. So they will be asking some analytical question like there is recalling question like why Dsb-Sc-Am modulator is called product modulator, because we are going to feed M of t and C of t to a local oscillator which is produced from a local oscillator. Just multiplying the same will produce us the output of a Dsb-Sc signal. Then what is coherent deduction? So why it is called as coherent deduction? Simple, there is a big question part. This is very important. They will be asking about what is Dsb-Sc-Am and they explain it fully, simply, or derive the mathematical equation of Dsb-Sc-Am. And also they can be asked with Dsb-Sc deduction and generation techniques. So if they are asking in general 13-mark question, you can choose any one of the generation and deduction technique, since time will be more if you write both the questions, which is nothing but 4 cases. So if they are asking generally, you can go with each one case. So they will be writing only 2 techniques of one for generation and one for reduction. Then explain how power is saved in Dsb-Sc-Am. We'll see it later. Hope you understood today's session of Dsb-Sc-Am under amplitude modulation. Thanks for watching. Our next topic will be the next case of single sideband suppressed carrier AM. Thank you.